So today we are continuing talking about sorting algorithms. On Friday, just for review here, on Friday we spoke about two sorting algorithms. We spoke about bubble sort and insertion sort, correct? Correct? Okay. And we said both those algorithms, what's the worst runtime on them? Yeah, n squared, right? Quadratic. So we said the worst case scenario is big O of n squared, right? So that here is the time complexity. So that was the time complexity of our two sorting algorithms. Anybody recall what's the space complexity on those two algorithms? Constant, very good. So we had the space complexity, and why was it constant? Because it's in place, right? So space complexity here, we said it's constant. Does not use additional memory. Sorts in place. Any questions with what we did on Friday? Yeah. Any questions? Okay. So today, what are we covering? Today, we are covering faster sorting algorithms. Today, we are covering QuickSort. And we're covering merge sort. Immediately, the differences between those two sorting algorithms and what we did on Friday, QuickSort and merge sort both uses what's known as divide and conquer algorithms. So here, both uses divide and conquer. Approaches in sorting. So, yes, sir.
Was insertion sort, was that logarithmic? Because we were going over like logarithmic on Friday, and I don't remember if that was.
I mean, an average or best case would be logarithmic there, but the worst case is quadratic, right? Okay, so divide and conquer, what's divide and conquer? Basically, both QuickSort and merge sort, what they do is they break up that array in smaller chunks, right? So every iteration of going through it, QuickSort and merge sort, it divides the array up. For merge sort, it divides the array up in halves. For QuickSort, it divides the array basically in 3 parts, right? Including what's known as the pivot, right? So there's a pivot for QuickSort, and the left and the right side of the array. So if you think about it, it's 3 parts of an array, or 3 parts in that array, right? So both of those sorting algorithms are much faster than our bubble sort and our insertion sort. And at the end, we'll see that the runtime here is big O and log n. There's some caveats in that there, but runtime, big O, and log n. And anytime we see log n, think of divide and conquer. I'm taking this problem, I'm breaking it up in smaller parts, right? Anytime we see logarithmic time, think of binary, where I'm breaking it up in two sections. So every time I have a smaller section I'm working with, right? That takes us to a faster algorithm. Okay. All right, so we have some context here. We could talk about QuickSort now. So QuickSort, what does QuickSort do? QuickSort uses a pivot, right? There's many ways to get a pivot with QuickSort. Some of the ways to get a pivot, I'll just put it down here. So QuickSort uses a pivot. This pivot is used to partition. Partition means separate. Partition or separate the array. Right? So immediately, anytime we think of QuickSort, we should think of a pivot, right? We use that pivot to partition the array. And that particular array will be partitioned into 3 sections, including the pivot. I'll just write up a simple example here. So if I have an unsorted array, and in our example, we'll be using one of the partitioning models called Lomodo. In Lomodo partitioning, you pick the last element. So for example, if I pick my last element here, being 10, minus 10, sorry, I would go ahead and partition the array. So the array would be partitioned such that I grab a section of the array before the pivot, and I grab the section of the array after the pivot. But in that example here, after the pivot, there's no elements. Everybody with me? So at that point, there's nothing to sort. There's nothing to sort to the right of the pivot. Everybody with me? Right, so the pivot would be, in our case here, this would be the pivot. Using, using Lomodo's partitioning. We pick the last element as the pivot. Right. There's other partitionings. There's partitionings where you pick the first element. There's partitionings where you pick a random element. And in our example we'll be using today, that partitioning will be picking every time I go through recursively. That's how we'll be solving our problem. Every time I recursively go through my problem to divide it, I always pick the last element with that particular algorithm, right? We're not just picking out of a hat what algorithm we use to solve QuickSort, right? Lomodo came up with the Lomodo algorithm to get a pivot in QuickSort. So that's what we'll be using. That's the approach we'll be using. But there's many other approaches. There's Lomodo. There is also Horace, H-O-A-R-E-S partitioning. And there's Dutch flag. So those are the partitions we have. We have Dutch flag, Horace, and Lomodo. And then you could pick the middle as well. That's also one of the examples you could use. In our lesson, we have the middle element being picked as that pivot. Yes, go ahead.
Why are we using Lomodo for that?
That's one of the more traditional approaches to introduce QuickSort, right? So that's the one we'll be using, right? We don't have the time exactly to go through each one. There's more reading on the lesson about each approach. But the approach we'll be using is to use the last pivot. Okay? But to keep it less complex as we introduce in QuickSort, I want us to walk away. The objective of QuickSort here is to know that we use a pivot, right? We use a pivot. The pivot partitions the array. Everybody with me? Those are what we need to make sure we walk away from QuickSort knowing what the differences are. The pivot partitions my array. It uses divide and conquer. Right? Those are the key terms here. Pivot, partitioning, divide and conquer. Everybody with me so far? Okay. Any questions before we continue here? And the names are after the people that came up with them here. And there's more reading, there's more resources there if you want to go deeper into them. But again, the objective of today and the assessment is to know what's the difference, what makes QuickSort special, or what's the differences between QuickSort and say merge sort, which we'll see afterwards, right? So you need to walk away knowing that there's a pivot data that you use, right? Whether you take the first element as the pivot, the middle element as the pivot, the last element as the pivot, or a random element as the pivot. Everybody with me? And then as you go through that problem, as you go through the divide and conquer algorithm, we're using recursion to go through that array each time until we get to a base case. Okay? When we get to that base case, at that point, our particular array has been sorted.
Is the video helpful to understand this more?
Say that again.
The video.
Yeah, we'll watch a video, we'll make an example using an array like we did Friday, and then after that, we'll go into the code. Okay? All right, so let's go to one of the videos here. Is this the correct one I put on? So here, they're mentioning divide and conquer. It uses a pivot to divide the array into two halves, right? It uses recursion to break up the array each time. Here they're selecting the last element. In that case, it's 70 here. That's a pivot. Sorry. So here it swaps the elements if it's less than the pivot. Anytime it comes across an element that's less than the pivot, it swaps those elements with I and J. And I is incremented. If I do a swap, I need to make sure I increment I. And lastly, it swaps at the end. It swaps I and the pivot. Okay? All right. So we'll stop here. The video is on the canvas. We'll stop here, we'll do it manually. The video is on canvas, but now we'll do it practically using our paper or whiteboard. Everybody with me? Everybody with me? Okay. So let us get an example and we'll go through it. Anybody want to give us like 6 numbers here?
Well,
I could use the same numbers, I guess. Okay. All right, I'll just write down numbers here. So let's write an unsorted list, and then we'll go through it using the Lomodo's principle. So here we have an unsorted array. We want to sort that array using the Lamoto's partitioning. In that case, we'll be using the last element in the array. All right, so let's give some variables here. So this is my pivot. We start off with I and j. We walk the array. Anytime I say walk the array, I mean traverse the array. Everybody with me? Right? So I'll traverse the array using a variable j. Okay? So what we need to do, each time we walk the array, we want to see if what I'm currently looking at is less than the pivot. In that case, what is j currently looking at? What value is j currently looking at? What value is j on? 80, yeah? Wait.
You have both I and J on 80.
I and j are both on 80. What is the current value of j? 80. Okay. Now we need to, okay, how are we doing here? Monday?
We're still, let's see.
I didn't hear 80. I heard 13, I heard different numbers. Okay. Currently, j is looking at what value? 80. Very good. So is 80 less than 13? No. So in that case, we increment j. Okay? Currently, what is j looking at? 10. Is 10 less than 13? Yes. So we stop here. And as the video said, we need to swap. Right? Here we need to swap I and we need to swap I and j. Everybody with me? So here we need to now swap. We need to now swap I and j. Was there a question?
No, I got it.
So we need to swap I and j. Let me just put in 1. Swap I and j, and 2. What's the second thing we need to do? There was one other thing in that video if anybody picked it up. If we do a swap, we need to increment some value. We need to increment I. Very good. So here, increment I. Okay, cool. Awesome. So let's go ahead and do that. We'll just write the numbers again. So in that case, my 80, I need to swap my 80, so that becomes 10. That's 80 minus 9, 0, minus 11, and 13. And I, we incremented I, correct? So I now is at 80, and j is now at 9, minus 9 here. So far, so good? Okay, so we'll continue on. Is minus 9 less than 13? Yes, right?
I have a question.
Yes.
I is the index of smaller element. Y is the combination.
I starts with low. I begins at the low element. In that case, it was 80, right? So they both start at the same place.
But isn't like 10 lower than 15? Confused. I don't understand I.
We're not looking at I. What we look at is j. What's j's value? Is j's
So J
value?
should be before, I should be before J? What is I represent?
Let's go again from the beginning here. I have two variables, I and j. I walk my array with j, right? I compare j's value versus the pivot. If I need to swap, meaning if j is less than pivot,
Yes.
I increment I. The only reason I need I is to go ahead and increment I here.
Like, so I, it will be like some number which is.
Yes, it's a tracker. Both of them are trackers. We walk in the array with those two trackers. If we need to make a change, we increment I, meaning if we swap, we increment I. Okay? But j is that variable we're using to walk the array until we get to the end. And when we get to the end, we have to recursively call it again. But we haven't gotten there yet. Chelsea.
This one we're just finding smaller.
Say it. The goal is to sort it, but the goal is to always return a pivot, and that pivot, to the left of the pivot will have less values that's lesser than the pivot, in that particular example, but the end goal is to always divide the array until we're done.
Until it's in order?
Yes,
Oh.
using that particular partitioning algorithm. We haven't finished the first pass. After the first pass, we'll see what the array looks like, but we'll keep doing passes until we're done. Yeah, go ahead.
So J increments.
J increments, yes, until to the end. Exactly.
Does the distance between I and J increase if it does?
Doesn't matter. The distance, don't think of the distance as anything. If the distance increases, that means it's pretty much in order, if that makes sense.
Okay.
Because I haven't incremented I. Cool? Very good. Okay, any other questions before we continue? So where are we now? We are at I and J. Hopefully we haven't errored out here, if anything. Let me know if I missed anything here. So here we have I and J. Currently, J is at -9. We said we're comparing now. Anytime we add J, we compare J with we compare J with the pivot. My pivot is what number? 13 here in that case. Okay? Continue? Can we continue? Okay, so we agreed that -9 is less than 13, so we need to go ahead and perform a swap here. And again, let's just keep attention to anytime we do a swap, we need to increment I, correct? Correct? Okay, so let's go ahead and rewrite those values. So we have 10, we have -9, we have 80, we have 0, -11, and 13. My I now is here, and my J is here. So my J is looking at what value? 0. Is 0 less than 13? Yes. So I go ahead and perform my swap. So 10, -9, 0, 80, -11, 13. We need to increment our I. I is here. Increment J. J is here. So far, so good? Questions? Yes, go ahead.
So we're comparing J to the pivot. If it is less than it, then we swap and we increment both as we just increment the
J, exactly. Very good. Everybody heard Amini's question, or basically a reaffirmation of like what we're doing. So we increment J all the time. If we need to swap, we increment I. Only if we swap, we increment I. Okay? Cool. So J is here. We need to perform a swap because in that case, -11 is less than 13. We go 10, -9, 0, -11, 80, and 13. Our I now is here. Our J now is here. The last step we do, regardless, we now have to go ahead and swap 80 with the pivot. Everybody with me? Regardless, when I'm done with my walking of J, I need to swap I with the high value, or in our case, the pivot.
So I would always be larger than pivot,
In that particular case, yes.
but in any case,
It depends on where we are in our algorithm.
so if it's not larger than pivot, then you don't.
We always swap at the end. We're not checking at the end, we just swap it. So at the end of the day, the bigger value will be to the right, yes. The bigger value will be to the right. In that case, 80 will be to the right of the pivot. The new pivot will be I.
But if I was 12, we would still swap.
If I was 12, would we still swap? Yes, in that case. Because we're not checking. Okay? All right, so let's continue on. Last step here, we need to swap I and the high value. So we need to swap those two values. So our end result for the first pass, again, this is the first pass here. First pass. At the end of our first pass, our array looks like this. Our I is here. And we need to return I. So now we have a new pivot. So here we have a new pivot. And we return the index. In that case, our index here is 0, 1, 2, 3, 4, 5. Our index is 4. So we return index 4. So now we have a new pivot.
But 13 is still,
13 is what?
is still a pivot.
Yeah, 13 is the
So
pivot
how is
here.
that a new pivot?
Well, we return the new index, regardless of what the value is.
Okay, so it's a new index.
Yes,
But the same number.
The same numbers.
the same number for now.
For now.
For now, but we are done with 13. Let's continue. Let's continue. So now, if we separate our array, the pivot is 13. Everybody with me? Right? So the pivot is 13. To the right of the pivot, what value do we have? 80. To the left of the pivot, what values do we have?
10, negative 9, 0, and negative 11.
Okay? So at that point, 13 is sorted. We're not dealing with 13 anymore. Right? At that point, 13 is sorted. We are not dealing with 13 anymore. And if we look at 13, to the left of 13, it's not sorted yet, but all those values are less than the pivot. Do we see that? And to the right, all the values to the right is greater than the pivot. Right? So here, using recursion, at that point, we'll continue to break up that array. The first time we have our array, how many elements we have here? We have 6 elements. Everybody with me? Right? So now, as I'm breaking that array using divide and conquer, my array gets smaller. I have 2 halves to deal with right now. I have a right half, which is 80, right? And we have a left half, which has 4 elements. Everybody with me? All right, so let's continue on here. So we'll split this guy up. We'll split this guy up. Basically, if we look at 80, we don't have to continue 80 because we know at the end of the day, there's only 1 element here. So we could say this is sorted. 80 is sorted. I'll just use green to say it's sorted. And let's go ahead and do 10 minus 9, 0 minus 11. Using the same principle that we just did. Using the same principle, using the same pick the last element. Everybody with me? And do the same thing again. That's recursive. So first pass, and now we'll continue using recursion. Here we will continue using recursion. That's what we'll be implementing in code. So let's write our values again. We have 10, minus 9, 0, and minus 11. What's our pivot here? Negative 11. So we know what our pivot is, and we start off with I and j, same way.
You just said the pivot was 13, so now it's negative 11.
The new index, we're not returning the value, we return the index.
Which
And we use that, the index is 4 here.
So then wouldn't...
We use the index to split the array.
So what I'm saying, wouldn't, okay, so then we start at the index of 3.
Can I just
That being the new pivot.
We split the array. What we do, we use the new pivot, we use that index to split the array up.
Okay, so that's no longer the
That's
pivot.
no longer the
And
pivot.
now the index of 3 is the new pivot, not 4.
Exactly, exactly. So now the
Because you
new,
wrote new pivot as the index being 4.
well,
so
new,
13.
I'll keep it as new pivot because it is a new pivot. We use the new pivot to split the array up. We'll see that in code. So what we're doing, let me just elaborate what we did here. So how the way we split the array is using that pivot, right? What we say pivot minus 1. Let's actually elaborate here. Let's elaborate this. So how do we achieve with the left and the right side? We use that pivot.
Okay.
Okay?
And that becomes sorted and
Exactly. So the pivot becomes,
minus 1.
exactly. So what happens here, the pivot, I say pivot minus 1, which is the high part of the array. And the low part of the array, I'll just say low for now. And the right side of that pivot is pivot plus 1. Right? And then I have high here. So that's how I split. I use that new pivot to split my array up. That's what I need the pivot for. Okay? Tiffany, you had a question?
I don't want to confuse.
We'll do one more to continue, and then we'll see where we are at the end.
So, if you scroll up, right? So
Scroll
the
up.
Pivot, before the pivot was 13, right?
Here, yes.
Because
splitting.
It's the last
an
element.
empty array, right.
Yeah, yeah,
It's
yeah.
an quote unquote an empty array because there's no values that
Yep,
are there yet.
yep.
And then the original array that is technically a part of.
Exactly.
But then once you've actually gotten a value that's shifted over to the quote unquote high point,
Mhm.
that is why that pivot now moves.
Is used to split.
Right. So it moves, but I think the confusion is that we're thinking that because the pivot.
It's always 13.
Right.
No.
But
It changes.
That's what makes it confusing.
Exactly. It always changes as I go through that array. Okay? Like right now, I have two arrays. My pivot is not 13 anymore here. In the new array that I'm dealing with, that new array here. Right? That new array here, the pivot is no longer 13. There's no 13 value here. I use the last element. My last element is negative 11. Chelsea?
Is there a tracker on the pivot too, or we're using the index, the I variable?
Every time we go through it, there's new values. Like in that case, our new value, our low value is 10, and our j is 10, right? And then again, our pivot here is minus 11. So every time we go through the array again, the values are changing. The variables are changing.
So for this specific one, we started with 80, and then the second number was 10. So 80 got brought all the way to the end.
Yes.
But it happened to be the largest number. If 10 came first and 80 was second, wouldn't 10 get carried all the way to the end? Because it's
Can we do that example after we do that first example? Because I don't want to do too many examples on the same thread. You had a question, May? Okay, so let's continue with that left side array. So we have I and j. What's happening here? Walk me through it. What are we doing? See if 10 is less than negative 11, right? And if it's not, what do we do? If it's not less,
Oh, if it's not, then we just.
in that case, if it's false, we do what?
Just increment.
Just increment j, right? Everybody? Okay. Is minus 9 less than minus 11? No. Is
Wait, go up. Is it supposed to be minus 10 or it's regular 10, right? And you said is 10 less than.
minus 11.
Okay.
Always the pivot. We always check in the comparison between what j is and what the pivot is.
Okay.
Very good.
Try comparing like minus 9 to minus 11 instead of 13 as pivot.
Say that again.
You said like it's minus 9.
Less than minus 11.
Why minus 11 and not to pivot, not to 13 anymore?
We clarified that earlier. We said every time we go through a new array, we have a new pivot. In that case, only look at that array
So
we're dealing
right
with.
now our new pivot is minus 11?
Yes. Very good.
Isn't it, if the pivot, if 10 is less than the pivot, or if j is less than the pivot, we swap?
If, in our case, is 10 less than minus 11? Is 10 less than minus 11?
No.
What do we do?
So we just increment.
We just increment. Is minus 9 less than minus 11?
No.
We increment, right? Now we're on 0, right? Jahid is, what do we do here?
Keep walking
We keep walking. Why?
because the values are they're all greater.
Okay, cool. So at this point, we add j.
What happens from 13?
Every time we break our array, our variables change. Earlier when we started off, right, we returned the index of 13 as the pivot. We use that pivot to calculate how do we split the array up, right? Once we split the array up, we no longer care about what 13 is. We go and we look at those new arrays we have. And we do the same thing we did from the beginning.
So we're looking at, what about
80 is sorted already, right? 80 is sorted already, and we keep green. We made it green so we know it's sorted here. So now we're only dealing with the left side, which is not sorted. 1.
So we have 2 arrays.
We have 2 arrays, yes. At the end of the day, yes. You could think about it like 3 arrays, the pivot, but the pivot in that case is sorted already. We don't care about it anymore. 13 is sorted. Okay? That's the base case for our recursive call. And now we have our left side. We, at the point where j has gotten to the last element. 1, what do we do now?
got into the last element.
Yes. Let me just scroll up here.
I guess we will swap the pivot with I.
Yes, very good. So everybody heard what one said here? So now we're going to swap I with the pivot, or the pivot with I in that case. And we'll have a new value that looks like this. So we'll have, well, not 10. We'll have minus 11, minus 9, 0, and 10. And where's our I? This is our I here.
So when we get like.
So what are we returning? We're returning the index. I is the index. We're returning, what's the index here? 0. Yes?
Once you swap the first and the last D, you don't have to go through it anymore, right?
Well, we're not done, right? We have to go through the whole algorithm again. Like, we're not done, right? Like, let us figure out what we're returning. Let's figure out what our pivot is, and let's figure out what's the left or the right side. Okay? So here,
I'm sorry, I missed why you switched again with minus 11.
the last step in the algorithm says you need to switch I with the pivot.
Okay.
Make sure we write that down. Okay, so now we at I. Let's use our color here. So this is the pivot. And we said the pivot here is sorted. And now we look at, we're using the pivot. We'll say pivot plus 1 is that index after the pivot. So here we have this array.
So what is it right now 10?
Yes, in that new array. Exactly, exactly. So we get in there. Very good. Any questions so far?
Yeah, so is J and I the indexes or not the?
I is the index we return. J is the variable we use to walk. So now we have 3 elements in our array. Let's continue on. And everything in green has been sorted already. So here we have 13, we have 80 to the right of it, and we have minus 11 to the left of it. Let's continue with this last array. Minus 9, 0, and 10. Where's our I and J? I and J is negative 9, very good. And our pivot is 10. Everybody on the same? Everybody here, right? We're looking at the new array here. So let's continue on. Is minus 9 less than 10? So we swap. Basically, we don't do anything here. But what else do we do? We need to increment both of them, correct? Is 0 less than 10? Again, we increment in both because we're swapping in the same place here. So now we have I and we have J. Okay? And if we swap I in itself, it's the same value. Everybody with me? What index are we returning now? Index 2. Very good. Index 2 is this guy. 10 is sorted. And that leaves us with our left side, which is not sorted. Right? Again, if we take a look at our green values, minus 11 is to the left of 10, so we are doing good. Let's continue on to minus 9 and 0. We have I and J. Is minus 9 less than 0? So we go ahead and we swap it in place here. We increment I, we increment J. Again, we swap I and the high value, which is the same value. And now we return I. And basically, we are done. Let's just make sure that we are good here. This is minus 9, and this becomes sorted. Okay? So to put everything back into place, let's look at our values. We have, to the left, we have minus 9. Well, we have minus 11 there, sorry. Minus 11, minus 9, 0, 13, well, 0, 0, 10, 13, and 80. Right? So at the end of the day, we sort it in place. We're not written in a new array. So everything we're doing, all the operations we're doing it in place. So at the end of the day, the array, when we have our base case, it will be sorted because we're doing everything in place. Everybody with me? I mean, yes, we have to diagram everything here, but if we do it in place, all the values will be in the correct position. Okay? So at the end, we'll have our final values being minus 11, minus 9. We have 0. Do we have a 10 here? We have 10. What's the other value? 13 and 80. So this is our final array, which is sorted. Okay. What we'll do the code example of this, and in the afternoon, I want to make sure that we do it by hand again. Do it by hand again so we understand the concept of it. But the big walkaway is knowing that we use a pivot, and we always have a different pivot every time we break that array up. Everybody with me? Okay? So let us continue on here. We'll be using the same pseudocode to map out our algorithm. Let's go to Xcode. Do I have an Xcode open? Xcode. Open up a playground, new playground, and call it QuickSort. New playgrounds. New playgrounds, and we are calling it QuickSort. Any questions? Questions?
Sorry, can you go back to it for a second?
Yeah, 1 second. Here? Okay, I'm back here.
Scroll up a little bit. So here, why is I incrementing when
Because we did a swap, right? Even if we swap the value of itself, we have to increment I.
swap?
We will add the same value. I and J was at the same value, and then there was a difference there. It was smaller than the pivot. We had to swap it. So basically, we swapped the value of itself. Okay, so we have a new playground. What are we doing? We are talking about QuickSort. QuickSort implementation using the Moodle's partitioning algorithm. Okay, cool. All right, let's just continue on. So QuickSort uses a pivot. In our example, we use the last element as the pivot, right? Last element as the pivot. Using this pivot, we split the array to the left of the pivot and to the right of the pivot. We'll put an example here. What example did we have? We had, so for example, if we have 10 minus 9, 0, minus 11, 10, 9, 0, 11. And our pivot was 13. And then to the right of that, we had 80. Right? So that gives some context here. And we said QuickSort uses divide and conquer approach to solve the sorting algorithm. Divide and conquer is split splitting the problem in half on every iteration or recursive call. Here I'll put runtime. One second. And log in. What was that, Luba? No, I just grabbed out one of the examples for us. Like when we got the new pivot, how we split the array.
So that's really after the process?
Yeah, that's after the initial process. Yeah, exactly. Yeah. I just wanted to take us directly to how we split that array up. We split that array up using the new pivot index, right? To the left of the index and to the right of the index.
Alex, what's the logic behind this though? Like, we're set for
To have smaller parts of a problem to solve.
using like
Recursion. So every time we get to that smaller problem, like 80 for example, we're not splitting 80 anymore because we're done with 80. Right? And as we go to the left, those 4 elements, we will end when we get to 1 element. So every time we split the array up. That's what the algorithm uses. And that's why it's going to be more efficient. Yes, it took us more, we wrote more, but runtime-wise, it's faster than what we did on Friday. Okay? It might be easier to conceptualize what we did on Friday, but this here is more efficient in the way it breaks the problem up. Because if you have 20 elements, you'll see bubble sort takes anywhere from like 100, 200 times it will take to run that algorithm, right? As opposed to what we have today. Okay, cool. So let's continue on. So here we will implement the modal partitioning. We'll have a function. We'll call it Lamodo partition. Okay, so what does our function definition look like? It needs an array to work with. As we said, we'll be doing that partitioning in-out like we did using our whiteboard today. It's an array of integers. And here we're returning an index. Returns new index, which we will use as the pivot to partition the array into a left and right side array. Okay? So here we have an array. We also need a low point like we did earlier, and we need a high index. So what's that low index and what's that high index? So those are what we need from the caller. Whoever is using that particular partition, they need to give us those values. What's the low of that array? What's the high of the array? We'll start off by creating a pivot variable or constant. Our pivot constant will take the array, which is high here, because we're grabbing the last element. Using last element in array. No, we need to write 2 functions. One is going to be the partitioning, and the second one will be the actual function, the QuickSort function. that uses this partitioning. So each time it calls this to partition, get me a new index, use that new index, split my array, do it again until we're done. Okay, cool. So here we have our pivot. We'll have a low variable or I variable, which we'll use from low. And this is the same I that we used, right? That's the same I value that we used. Everybody? This is the I we'll be using. Like if we have to swap, this is the I that will be incremented. Everybody with me? And this is the I or the index that will, this is the index that will be returning to wherever call us. That new index, for example, if we go back here to the diagram, if we go back to our diagram, this I represents, in that example here, 13. Everybody with me? Okay. Sorry. Okay, so we have our pivot, we have our I value, so now let's go ahead and iterate through the array. So iterate through the array using J variable so here we'll say for J in low to high. So now we iterate through the array, same thing that we did on our paper on whiteboard. We iterate through the array, okay? What's the check we do? What are we checking for? What's that? If J is less than pivot, right? In that case, less than or equal to.
So will I basically beginning and end of array?
I is that value will be returning, and that value will be swapping if there's a swap. I mean,
Low and high.
yes.
Low beginning.
Low is the beginning, yes, sorry. And here, low is a constant, that's why we made it a variable I, because low is a constant here in our function. Okay, so now we have, let's continue on. So if array, if the value at J is less than or equal to our pivot, what are we doing if it's less than or equal to? Before we increment, what are we doing? Swap, right? So we need to swap and increment I. So on our array, we'll say swap at. We'll just use swap at here. We saw how to do it without swap at. Everybody's comfortable with implementing swap at without this built-in swap at function? What's that?
I was gonna say we could do a pop swap at the first time.
Okay. So here we do swap at, and what are we swapping? I and J. So we're swapping I and J, and we're incrementing I. So I plus equal 1. Cool. So at this point, what's the last thing we do here before we return? Changing pivot and I. Very good. So now I need to say our array swap at change pivot with I, or high in our case here, because pivot is a value. We want to get to the actual element. Everybody here? I don't want to do pivot because pivot is a value. I want to do the index. That's why I'm saying high. Yulia? Cool. And lastly, we return I. So this is our partitioning algorithm. Right? Feel free to look at other partitioning algorithms and implement them there and see what the differences are. But here we'll be using our QuickSort. The QuickSort we're using will be implementing this partitioning algorithm that we have here, using the last element, right? So the model uses the last, did we say that anywhere? QuickSort pivot uses, for example, we use the last element. Here we could just say models, partitioning. Okay? All right. How are we doing so far? This is what we did manually on paper. Okay? So let's go ahead and write our last function. We'll call it QuickSort, the model. Our QuickSort takes in an array. which is also in out. We're doing it in place. An array of integers. We'll also have a low index and a high index. And here we're not returning any value because we are doing this in out, in place. Here we have to return a value because we're returning the index. Everybody with me so far? Okay. So in our quicksort algorithm, our base case, if low is less than high, we want to continue. What that means is, if I'm still looking at an array of multiple elements, let's continue on, right? So if low is less than high, we want to go ahead and get a new pivot. So get a new pivot. And how do we get a new pivot? Using the function we just wrote. We pass it the array. Again, our array is expecting to be in out. We need to mark it with an ampersand or an and symbol. Because that array itself changes every time. It's in out, it changes every time. It gets smaller every time. Okay? So here I pass low and I pass high. And now we need to go ahead and do our recursive calls. We need a left array and we need a right array. So both those arrays need to basically get to a count of 1 and then we're done. So in our left array, what does our left array look like? We call QuickSort. We passed our array. In our case, we'll pass low. And our high, let's go back to the example. We'll come back and code out. Let's just go back to the iPad real quickly to see how we achieve our low and our high. So our pivot currently is 13. Do we see 13 here? How do I split my array up? That's the big part we're about to do now. How do I split that array up? I say pivot minus 1 is my high value, right? And my low value is just simply low. How do I get to the right side of my array? I say pivot plus 1, right? And the high value in that case. So that's how we split that array up every time we call it recursively. So we need two arrays, the left array and the right array. And those are being called recursively on themselves. If I go back to my code here, so high, what's high here? Pivot minus 1. Okay, so that's the left side. And let's go to the right side. So QuickSort, we pass our array. Exactly, so pivot plus 1, very good. And what's the high? Simply high. That's how we split the array up. Again, we did all that manually. We still code everything. So now I have two arrays. And every time I call it, I check if low is less than high. Meaning if I'm only looking at one value, I'm done if I'm looking at one value. And since it's been done in place, there's nothing I need to return. There's no return here. Because everything is getting done in place. Very similar to like our bubble sort, our insertion sort. It's done in place. I'm not returning a new array. Everybody with me? Okay? And again, here, this is recursion. It's just calling the function again. And every time it's calling the function, it passes the array that's basically partially sorted. Every time it calls that, it's partially sorted and a smaller array until we get to an array where there's one element. And at that point, we are done. Because what's changing? The array is the same, but what changes is the low and the high values, right? So those change until I'm pretty much watching one value. If I'm watching one value, 0 is not less than 0. Everybody with me? If I'm looking at index 0, it's not less than 0. I am done. Let's put out an example. We could use the same example we had. What's the unsorted array here? Okay, so this needs to be a variable. We'll call it list, and we'll say 80, 10, minus 9, 0, minus 11, and we had 13, right? Okay, so we have our list. Let's go ahead and call QuickSort. which expects an array. Again, I'm marking it with an ampersand there because it's in out. Everybody with me? Questions about that? For my low, I'll pass in 0. In that case, 0 is 80, index 0. How can we achieve our high? Very good. So here we have list.count minus 1. Again, we don't want to pass list.count. That's out of bounds. Minus 1, as what Christian said here, will get us to 13, the index 13. So we pass index 0 and the last index here. And now we'll just go ahead and print our list. If we have any errors, we'll be able to take a look at it and see what's going on. So run this. And here we have minus 11, minus 9, 0, 10, 13, and 80. Right? Did everybody get that same conclusion with their final list, their final sorted list? Scroll up to the first function.
Yeah.
I mean, we have time. We could implement bubble sort and see on the same array how much time it's going to take given like a larger array and see what the differences are. Yeah.
So we put that the low is 0 because we know the low is 0, or just the low will always
Because we know we don't want given the function the array, we know an array of X amount of values, so we pass it 0 as that low value that we want to start with.
So now what if it's a situation where we don't know what that low
Then you'd find out what the count is and check against, like, is the count greater than 0, for example? And in that case, just pass 0.
Alright, so when the low and the high are what is the count?
Is the index. The low and the high is the index. So here we
Index 0 would mean that there's what, 1?
that's where I start looking at my array. That's where my I starts for the first pass,
Gotcha.
right? But it's gonna change as I get a new array each time.
And it knows that it's looking for an index.
The first time we pass the array, we pass 0, but everything else is taken care of by the function, by the recursive function. Because the recursive function, if you look at what low is here, low is not 0. If you look inside that function here, the low changes based on what the array is. Okay? Yes? You could put in different numbers. Oh, there's a problem there. So let's look up, make sure you incremented I. That could be a problem if you don't increment I here. Are you incrementing I? Make sure you have your pivot array starts off as the high element or the last element, right? You move on, you say I is equal to low here in that example. We use J to iterate through the array, right? This is a close range. We're not including high, right? Next, we said if the current value we're looking at is less than or equal to the pivot. We swap if it is, okay? Then we increment I if we do a swap. Lastly, we have to make sure we swap I with the high value, not pivot. Pivot is just a value. We want the index here. So the index is high. So far, so good? Okay. Now we continue on to QuickSort. We say if low is less than high, right? If my low is index 0 and my high is index 5, I need to continue splitting that array. I go in, I find a new pivot using the Lomodo partition function we wrote. We pass in the array, right? We pass in low, in that case, whatever was passed to us in the function. We pass in high, because we're trying to get a pivot of that entire array. Next, we need a left array, so now we're splitting the array up. How do we split the array up? We split the array using the pivot, okay? So our low is low in that case, as we saw in the examples we did. Our high is what the pivot is minus 1. That gets us that index before the pivot. Next, we look at the right array. How do we create that right array? We create that right array using the pivot index plus 1, right? And high in that case is high to the end of that array on the left side, on the right side, okay? And then we have our list. We pass in 0, which is index 0 here. Index 0, I'm looking at my array. I'm the one passing that array. I pass in index 0, and I say the last element will be the count minus 1. And then I print what list is. Cool? All right.
I have exactly what you have, but it's giving me 13, -11, 9, 0, 10, and then 8.
There, it's not exactly right. There's something missing there.
Can
If
we
it was
start from
exactly,
there?
it would be the same thing. No, I didn't get the same results.
Okay, I got the same as you.
Is this supposed to be a real J instead of that, or is it just for J? That's what it is?
It's all there. Okay, let us go ahead and implement our word sorting algorithm and see what the differences are up here. No, that's good. That's the goal of this whole program. Okay, so let's go ahead and implement bubble sort and then see what the differences are here. So bubble sort.
That's so crazy. So how come it is that everything else was in order except for the pivot?
If you do it by hand, you'll see why. Because if you look at the wrong value, you're going to be moving the wrong thing.
But everything else was in order but the pivot.
Yes. Okay, so here we have bubble sort.
Thank you.
Thank you. So here we have bubble sort. From our signature on Friday, we have an array, integer. Oh, I need to, please somebody remind me, let's change this to generic after we're done here. So what does bubble sort look like? We say for in array that count and we use a j value to walk it. We're not looking at 0 here. And basically, what are we doing now? So we're saying if array at j is less than array value at j minus 1. So this is review from Friday, right? Yes? So if we come here, we say array.swap. And here we swap in j and j minus 1. Why am I having this error here? Exactly. So everybody, pay attention here. If I want to manipulate the array, that array is a constant. Right now, that array is a constant. To remove that or to change this, to fix this, we need to mark this as an in-out function. Everybody with me? Okay, cool. Let's just test out our bubble sort before we do anything here. We'll just say bubble list. Again, this needs to be a variable. Bubble list. 90 minus 8, 1, 2, 1 minus 90. And what's our question? Bubble sort, pass in our bubble list, and then print our bubble list. So our bubble list is sorted correctly. Minus 90, minus 8, 1, and 90. Right, everybody? So now let us populate at least maybe 20 elements and see what it looks like here between the two of them. So this is our worst algorithm, right? We started off on Friday with this one. It swaps adjacent values. It does it n squared. So this is n here, and this is n here. So n times n is n squared. So this. So this is the worst runtime, quadratic. So now our goal is to populate an array of 20 elements, same 20 elements on both algorithms, and see what the times are in our playgrounds. It will show us what the times are. Madam, did you test it already?
It's finished.
Did you test it?
-23, -8.
Did you put in like a 20 element array and test it? I see you texting with one finger there. You know I'm looking everywhere. How we doing? We good? Okay, so let's go up and how many elements we have here? We have 6, right? So I could just,
It could be the same numbers.
yeah, that's fine. We'll just paste this like twice. And I will copy this. So I have 18 elements here. I'll just make it 20 elements. So 78 minus 100. Just basically have 20 elements. It doesn't have to be what I have here. Everybody? Right? It doesn't have to be. But try to keep the same elements that you have on your first list as your second list. Everybody with me? So I'll copy my elements from my first list and I'll paste it on my bubble list here. So both have 20 elements. Both have 20 elements, both are trying to sort, and let's see what the outcome is here. So run this. So here I have 97 times it's running, and if I see here it's 14 times, right, 67 times here, doing the swap, right? So already we see if we start increasing this particular number, right, that gets a really bad place really quickly. So say like I have 100 elements, 200 elements, 400 elements. Before you know it, Playgrounds is going to crash. Okay? So again, to iterate, we're not talking about bubble sort. Bubble sort is one of the worst algorithms here. Worst sorting algorithms. But knowing how to implement it, I've seen it in interviews. Please know that implementation. And know why it's slow. So, to reiterate what we did today, I want us to walk away knowing that QuickSort uses what? What does QuickSort use? Walk me through QuickSort. N log n, that's the runtime, right? If you pick a wrong pivot, by the way, that becomes quadratic. Just keep that in mind. That's why we try to stick with algorithms that's proven already, right? Like low model. But again, Amini, what does QuickSort? Walk me through QuickSort, the fundamentals of QuickSort. It uses divide and conquer. It uses a pivot. What does a pivot do? The pivot is used to partition. Use the word partition. So the pivot is used to partition my array in 3 sections, including the pivot, right? And then we use recursion to make for that divide and conquer approach, right? So those are what we need to walk away with. And then the implementation we used today was in place. We did not use any extra storage to solve the algorithm, right? If we look at our lesson notes, it uses the middle index. It might be an easier one to conceptualize, but it uses extra space there. If we look at the lesson notes, it uses extra space, right? There's new arrays being created. Everybody with me, right? So at the end of the day, this is more efficient. It does not use any extra space, okay? All right. But if you were somewhere and somebody like, oh, do QuickSort and you forgot what the model looks like, take a look at what the lesson notes are. Everybody with me? Everybody with me? Right? So if you're stuck, interview, you're trying to figure out QuickSort, somebody tell you to implement it, you forgot what the model looks like, you could just use the middle pivot, the middle index, and use space. But in that case, if the person say, oh, you cannot use space, right? Then there would be other questions there, right? But know that what we implemented does not use any extra memory. Space complexity is constant, okay? All right, so we'll end here. Any other questions so far? Again, this part we did together. Please do it again later during lab time or some point, right, before assessment. This is a good thing to practice. Do it by hand. Doing it by hand, you'll understand this way better. Do it 10 times. Do it by hand. Use five elements, 6 elements. Get to the partition. Break up that array until you get to a sorted array. Then go back and implement it. Walk through the model partitioning function, right? Because those are one of the things, you saw it today for the first time. We did a lot here, right? But to really drive it home, you have to practice it manually or whiteboard, pseudocode, whatever, and then implement it in code, right? Everybody with me? Okay, cool. So we'll stop here.